All right, hi everyone. Welcome to my office hours. Today we'll be going over chapter 5 and maybe going into some of chapter 6. I just know that chapter 5 is a really big chapter that a lot of people have issues with, so I'll probably be focusing on it more and then maybe briefly go over chapter 6. Okay, so chapter 5 is all about stereochemistry, and all stereochemistry is how the molecule is oriented in space. So like if you look here at this guy right here, let me get my annotations out. If you look at this guy right here, this is a tetrahedral molecule. This is a representation of a sp3 carbon, which essentially means a carbon with 4 different electron groups around it or 4 bonds. This will become more important when we're talking about chirality and chiral centers, but this is generally the shape that we'll be talking about today and in stereochemistry as a whole. And the way that we generally represent this structure is we have 2 lines, one solid wedge and one dashed wedge. The solid wedge represents what's coming out towards us, which is the green one in this case. The dashed wedge represents what's going behind the molecule, which is the yellow molecule in this case. And the lines are just showing us what's in plane or what's in the plane that we're looking at. So you can see here that this guy is pointing straight up and this guy is pointing to the side, and neither of them are pointing towards us or away from us. So that's why we generally have 2 lines and one solid wedge and one dashed wedge. Okay, and this is generally the representation you'll see when I talk about it, because I don't know, I'm not exactly, I can't draw this every single time. Okay, so let's continue on. So what we're talking about here is the difference between constitutional isomers and stereoisomers. Stereoisomers are isomers that look exactly the same as far as connections go. So like the carbon's always going to be connected to an oxygen, the oxygen's always going to be connected to a hydrogen, but the way those connections are in space can be a little bit different, okay? So it's sort of like the big example that I see a lot of people doing is your hands, they look exactly the same. You have the same type of connections to your pointer finger, your middle finger, and so on, but they're oriented different in space because they're reflections of each other that cannot be superimposed. What do I mean by superimposed? Well, I mean that as much as I twist one hand, I cannot make it go directly on top of the other without physically flipping it again. Okay, so that's what we mean by different stereoisomers. They exist differently in space, and when we're talking about non-superimposable images, we're generally talking about enantiomers. But the hand example is one that a lot of people will talk about. I think chiral means hand in Greek or something. I listened to that on a Khan Academy when I was in your shoes. Okay, so we can see here that we're starting here with cis and trans isomers. So essentially, cis and trans isomers exist when we have one guy that's cis versus one guy that's trans, but they look exactly the same as far as connections go. So for example here, this guy is cis, this guy is trans, this guy is also cis. So we can sort of think of these two as exactly the same, because if both of these are pointing forwards, and let's say that we just turn this molecule around, both of them would end up pointing backwards like this. So they're the exact same molecule, okay? Here, on the other hand, one is pointing forwards and one is pointing backwards. So even if we flip it around, this one would end up being a dashed wedge and this one would end up being a solid wedge, and it would still be trans. So this is the same as this. Okay? And so they're stereoisomers of each other, but these two are the same and these two are the same. Okay? And then that's the general idea between cis-trans isomerism. There's also the idea that cis-trans isomerism can exist when we're talking about double bonds, which you may have seen in your homework. So let's say we have a double bond right here. So both of these have CH3 groups on it. One is pointing up and one is pointing down. So we consider this trans. And then in this case, one is pointing up, the other one's pointing up. We consider this cis. So this is another example of cis-trans isomerism. We just usually don't refer to these specifically as cis or trans for information or for reasons that will be more clear in later chapters. Just know that if you see these guys, these are stereoisomers, because if you think about it, when you have a double bond, you cannot rotate freely about that double bond. So what that means is this one's going to stay, this CH3 here is going to stay up, this CH3 is going to stay down. They can't flip-flop and become this molecule, okay? So that's another type of cis-trans isomerism that you might see in your homework, but I personally think that this type of cis-trans isomerism in the top right will be the one that's more focused on, okay? So now let's get to chirality. Again, we can see here the example with the hands. This always confused me when I was a student, but once you get it, you get it. So if we look at this guy here, as much as we try to rotate him to become this guy, like if I rotate him around to, it would end up looking like this. Oh God, there's my hand. It's your thumbs are on the same side, but your fingers are pointed downwards. So you're never going to look the exact same as this hand if you're this hand. That means they're non-superimposable. However, and this example always confused me as well, if we end up rotating the sock around, it will be superimposable. This example I don't generally like. I think more of an example that would help me is like, let's say we have a circle with a line coming off of it, and I draw the mirror image. We can twist this guy so that the lines line up and they're the exact same. So these are superimposable. This one's a little bit harder to see, so I don't really like this example, okay? Okay, so superimposable means we can twist the molecule around without flipping it to make our superimposable mirror image, okay?
Question.
Somebody has a question?
Yeah. If they're superimposable, does that mean they're identical?
Um, yes. Yes, I think so. I'm trying to think of any examples where it wouldn't be identical, because it's whenever you're talking about science or organic chemistry in general, there's never like an always or a sometimes. Generally, yes, if they are superimposable, you can consider them identical.
Okay. Thank you.
Okay, no problem. So now we're going to be talking about chiral versus achiral. Achiral means not chiral. That means they are superimposable. Chiral means they are not superimposable. So like we can see here, this picture is sort of hard to see, but if we draw it using the dashed wedges and stuff, we can see here that the red is on a solid wedge, the yellow's on a dashed wedge, the green's on a regular line, versus, ooh, let me uh, put colors on these so it makes more sense. And then, here we go. And then if the other one, if I were to draw the other one, um, yeah, sorry, I don't draw these super fast, just because, I don't know, I'm not used to drawing them all the time. Eventually, you'll probably be able to do this in your head, but as much as I try to rotate these guys, like if I try to rotate it so the greens are in the same position, this guy standing straight up would end up pointing down. They are not superimposable, okay? Okay. So let's go on and talk about planes of symmetry. Usually when we have a plane of symmetry, we're going to be achiral, and this will be more important when we talk about meso compounds. It's just recall here that we see carbon with a plane of symmetry, like a single carbon here with a plane of symmetry, which means both of them have hydrogens on either side or another molecule. They are achiral and they are superimposable. Again, this will be talked about more when we talk about meso compounds. Okay, so now let's talk about stereogenic centers. Generally, stereogenic centers are carbons with four completely different groups attached to it. These different groups can be anything, honestly. So like, let's say this yellow one's a hydrogen, this pink one's an OH, and then this orange one's a CH2, CH3, and then this purple one is a CH3. Even though the purple and the orange are both attached to a carbon, these groups overall are different because this group is a methyl group and then this group is an ethyl group, which makes them different and it makes them react differently. So this carbon would be chiral. It has 4 different groups. Now, when we look at something like this, it's not completely obvious if we have a chiral or a chiral carbon or not, our stereogenic center. So what I usually did is I would circle the carbon and I would count the carbons coming off of it. So on this side we have 5 carbons. On this side we have 4 carbons. So these 2 are different groups. This Br is a different group. And remember, we do not draw on the hydrogens generally when we're doing a line angle structure. So there is a hydrogen attached to this carbon. It's just sort of invisible. So yes, this carbon here is a stereogenic center. However, this carbon here is not because it has 2 hydrogens attached to it. Okay? And so what's important about these chiral centers is we can assign a particular configuration to them called R versus S. And the way that we do that is we have to assign priorities. And the highest priority is going to be 1, in this case that would be chlorine, and the lowest priority is going to be 4, with the others following that. So the priorities go 1, 2, 3, 4, decreasing. And so how do we assign priority? We assign priority based on the mass associated with the molecule. What do I mean by that? So what I mean by that is the first thing we look at is the atom that the chiral carbon is directly attached to. So in this case, we have Cl, oxygen, carbon, and hydrogen. Okay? Cl has the highest mass, so it's going to be the highest priority. Hydrogen has the lowest mass, so it's going to have the lowest priority. Most of the time, a regular hydrogen is going to be your lowest priority. Okay? There is a version of hydrogen that you might see that's called deuterium, which is just a heavier version of regular hydrogen. So let's say that instead of this group right here, we have deuterium. That is considered a different group from hydrogen. So if you have deuterium and hydrogen on the same carbon, that carbon is still going to be chiral. Okay? So back to assigning priorities. So after we assign priorities, what I usually do is I ignore 4 and I go 1, 2, 3, and I see if it's going clockwise or counterclockwise. Okay? So this one in this case is clockwise. And which one is clockwise? RS. R is clockwise. S is counterclockwise. Okay? So if this were just a regular molecule, let's say that instead of having the hydrogen on a solid wedge, it would be on a dashed wedge because that's something that I want to get into later. So let's just imagine that this chlorine was on a solid wedge and we're going clockwise. We would consider it an R configuration. Okay, so let's do a quick example that I'm going to make up off the top of my head. So let's say we have this guy right here, and then we'll make that one here, and then this guy right here. So now we come into a problem. We see that these 2 groups attached to the chiral carbon, both are made up of the same atom. Both of them are directly attached to the chiral carbon with another carbon. If that is the case, if the atoms are exactly the same, then what we do is we look at what that atom is attached to and see which one has the higher mass it is attached to. So like for example, this one's attached to 3 hydrogens, this one's attached to 2 hydrogens and 1 carbon. This guy has a higher mass overall, so this is going to be a higher priority than this guy. So bromine's going to be 1, this one's going to be 2, this one's going to be 3, and hydrogen is going to be 4. Okay? Now, let's say instead of having only hydrogens attached to this carbon, let's say this guy had a chlorine attached to it. Then this guy would become the second priority because it's attached to a higher mass. So this carbon is attached to a higher mass atom, so it's going to be higher in priority. And so then this is the rule that we're generally going to follow. Like if let's say that this was attached to another carbon here, then we would go to the next atom because both of them would be attached to 1 carbon, 2 H's. 1 carbon, 2 H's. So then we would go to what that one is attached to, and so on and so on and so on. Okay? So in this case, oh, I didn't want to do that. I want to erase them. So in this case, if I just did this guy right here, let me erase some of this stuff. Then again, let's say that it's 1, 2, 3, 4. I ignore 4, I go 1, 2, 3. That is counterclockwise, so this guy has an S configuration. And remember, the configuration is specifically for this chiral carbon. So like if I had another chiral carbon, then it would be, it would have a different configuration, so I'd have to have S plus whatever configuration the other chiral center is. And we'll discuss how we incorporate that into nomenclature a little bit later. Okay, and so now we come up to an issue where what if the lowest priority is not on a dashed wedge? So in this case, our lowest priority is hydrogen and it's not on a dashed wedge. So what we're going to do here is we're going to go back to that, let me scroll up real quick. We're going to go back to this idea of the tetrahedral molecule, okay? And all that we do is we're changing our perspective in order to put the lowest priority on a dashed wedge, to put the lowest priority in the back, okay? Okay, so let me clear that and let me go back down. So when we have the lowest priority not on a dashed wedge, so that means it's on a solid wedge or on a regular line, which is in this case, what we do, or what I like to think of it is, I like to think of it as I grab something, I hold it steady, and I twist the whole molecule around it. So this guy, for example, this guy is going to stay steady. So I'm doing a different method than this way, but I prefer my method because it just seems a little bit simpler. So in this case, I'm going to hold this guy steady, and I'm going to turn the whole molecule around so that I put hydrogen on that dashed wedge. So that means I'm turning the whole molecule around this way. So this guy will stay the same, and all of these will shift one position to the left. So CH2, CH3 stays the same. Hydrogen goes on this dashed wedge. OH shifts to go on this solid wedge, and then the CH3 shifts to go on the regular line. And so then we can look at our priorities from before, 1, 2, 3, and our fourth priority is on a dashed wedge, so we're okay, and we do this, and we see that it has an S configuration. Now, let's say that instead of having the hydrogen on a solid wedge here, it was on a regular line right here. So let's say that the H was right here, the CH2, CH3 was right here, and the CH3 was right here. So instead of holding this line steady, let's say I hold this guy steady and I turn this whole plane around clockwise. So the H, so I'm holding CH2, CH3 steady. I move the hydrogen to this dashed wedge. I move the OH right here, and then I move the CH3 right here, and I do my priorities again, 1, 2, 3, and we can see here that this one is R. And so let's go back to this beginning one, and let's see what the configuration would have been if we did not swap. It would have been 1, 2, 3. It would have been S, okay? Notice here we're swapping from S to R. So generally a good rule of thumb to have if you don't have time to do all of this is to say if the lowest priority is not on a dashed wedge, whatever it is, you're just going to swap it. Okay, so in this case it was S, so we're just going to swap it to R. Okay, and we can skip all this stuff. However, sometimes this isn't valid, and if you do have time, I would check with doing this method. Is everybody clear on this? Does anybody have any questions? Or are we all good? Again, we aren't actually changing any connections in the molecule. We're not changing, we're not swapping anything. We're just changing our perspective of the molecule, okay? Okay. I know he has a different method here. This method, it's not done. So he only did one step into this method. There should be another step. So like you see here, they switched the CH3 and the H, but then he was going to go and switch the OH and the CH2, CH3. It's just it's a different method from mine. I felt like mine makes more sense in a three-dimensional way. It just depends on how you think. This way works just as well. It just depends on what you prefer. Okay? So enantiomers and diastereomers. So enantiomers are something, they are a non-superimposable mirror image of a molecule. Okay? And then diastereomers aren't superimposable either, but they're partially superimposable. So like if we look here, so these are a pair of enantiomers, and these are two different pairs of enantiomers. If I take one pair from each, or if I take one from each pair, they would be considered diastereomers. Because looking at the pair that I've designated here, this OH is imposable on this OH, but this methyl group is not superimposable on that methyl group. So diastereomers are partially able to be superimposed, and enantiomers are not superimposable at all. Okay, that's the main difference. Now, how do we tell if something's an enantiomer or a diastereomer? I always had trouble doing it in my head, figuring out if they are superimposable, if they're partially superimposable. So what I always did is I looked at the chiral centers. So we can see here in these enantiomers, the chiral centers become complete opposites. This 1R becomes a 1S, this 2S becomes a 2R. This 1R, this 2R becomes a 1S, 2S. However, if we look at diastereomers, only part of them swap. So let's look at the example that I did before with this one and this one. We can see here that 2S swapped into a 2R. However, 1R stayed 1R. So part of it flip-flopped, part of it stayed the same. And this makes sense because if this guy doesn't change at all and if it stays superimposable, then its chiral center is not going to change configurations. However, this one did swap, so its chiral center has to change. Okay? Okay, so let's see. So for every pair of for every pair of enantiomers, there are a bunch of other diastereomers, and the different types of stereoisomers there are is we use the formula 2 to the n, where n is the number of stereogenic centers. So this molecule has 1, 2, 3 stereogenic centers, 2 to the 3. That equals 8, and we can see here we have 1, 2, 3, 4, 5, 6, 7, 8. So that works out. Okay? And we can see here, all of the enantiomers are paired up, but if we take any pair from two different pairs of enantiomers, they're considered diastereomers. Okay? Let me see if I can find a good example here. So yes, let's look here. So this one's naming diastereomers. I'm going to draw two things, and I need you to tell me if they're going to be diastereomers or any. Actually, I'll just do it myself because I don't know. I feel like participating is just really nerve-wracking for me personally, and I don't want to do that to anybody else. So let's do this guy right here, and we'll do this guy right here. And so essentially what I'm going to do is I'm going to do the stereogenic centers. So there's a stereogenic center here, which corresponds with this stereogenic center here. And then there's a stereogenic center here with the BR that is going to correspond with a stereogenic center over here with the other BR. And so I'm just going to do them one at a time. I'm going to assign a priority. So chlorine has the highest priority, and then this group, and then this group. I ignore 4, but it would be a hydrogen right here. And we'd say this is RS. I'll give you a second to think for yourself. It's counterclockwise, so it's S. I know I had a lot of trouble remembering which one was which, so I try to give you guys a chance to answer in your head, but I do want to make sure I get through everything. So just to reiterate, this guy here is S. So now we're going to do the green stereogenic center here. BR is 1, this group is 2, this group is 3. If we do this, this is anti-clockwise, so it's S as well. So I'm going to erase this. And so now we have our stereogenic centers. And the way that we would write this as if it were a name, we would say the stereogenic center on carbon 2 is S, and the stereogenic center on carbon 3 is also S. Okay? So now let's look over here. Let's look at this one. Chlorine is 1, this group is 2, this group is 3. It's still on that solid wedge, so nothing changes. it stays S. So we still have 2S, okay? However, let's now look at this other one here. All of the priorities are the same, so 1, 2, 3. It looks like S, but we see here that if we draw out our lowest priority, it would be on a solid wedge. So we're going to transform this into an R. So this would be 2S, 3R. We can see here that 2S did the same, but 3S, 3R swapped. So these are diastereomers, okay? And so now I want to get into naming these guys. Essentially, when we name these guys, at the beginning of the name, we're going to add parentheses. So parentheses. And we are going to put in the number of the carbon that's the chiral center, and then whether it's R or S. So in this case, we had 2S, 3S, I think, if I remember correctly. Okay? So 2S, 3S, that's all we add on to do our stereogenic center. And if we look here, our parent name would be pentane because we have 5 carbons. We have 2 chloro, 3 bromo. So to do that in alphabetical order, it would be 3 bromo, 2 chloro, oh god, I'm running out of room, pentane. Okay? And so then that's how you would name something with stereogenic centers. Somebody asked in the chat, can you assume right away that they're diastereomers when only one thing is different? Usually, yes, but I wouldn't make that your rule because, again, we're talking about diastereomers. They're partially superimposable, but I've always found, for me personally, the more surefire way to see if they are or if they are not diastereomers is to look at the stereogenic centers, because sometimes I would mess up because I don't see things three-dimensionally very well, if that makes sense. So I'm going to give a few examples of different stereogenic centers, like different pairs of stereogenic centers, and I'm going to tell you if they're diastereomers or enantiomers. So let's say we had something with 3R, 2S versus 3R, 2R. This would be considered diastereomers. One stayed the same, one changed. 3R, 2S versus 3S, 2R. That looks like a 5, but at 3S, those would be enantiomers and so on. And so then that's sort of what I would do on a test to figure out if something is a diastereomer, an enantiomer, or completely different compounds or the same compound. So now what we're going to do is we're talking about meso compounds. Meso compounds are defined as an achiral compound that has a stereogenic center. So we see here in this case, we see that here's a stereogenic center, here's a stereogenic center. And why are they stereogenic centers? Well, we see here that this carbon is attached to an OH, a hydrogen, and it's attached to 2 carbons, but they're part of the same ring. However, those 2 carbons have different connections. This carbon up here is connected to an OH, a CH2, and another H. This carbon right here is attached to 2 H's and then 1 C, so they have different groups. It's a chiral center. So again, here's one chiral center, here's another chiral center. Meso compounds will usually have an even number of chiral centers. It depends, but you have to have more than 2 because you have to have this plane of symmetry. Somebody said, I thought meso compounds wasn't a way to describe a relationship between 2 things. You're right, but you should be able to say, oh, these are the same 2 things because they are a meso compound, if that makes sense. So like these 2 are the same structure, they're the same compound because they are meso, if that makes sense. So like if you see here, this guy has a plane of symmetry and this guy has a plane of symmetry, so they're the exact same. And so would these be considered identical if asked what was the relationship? Yes, although sometimes they will include meso compound as like a choice. So like for example, if they only had enantiomers, diastereomers, or meso, then you would say, oh, these are meso compounds. Otherwise, I would say they're identical because they are. Okay? And the reason why they're identical is that you can sort of imagine how, oh, these 2 are forward facing, these 2 are backward facing. All you did was flip this around so that these would be in the back rather than in the front. Okay? Yeah, no problem. Okay. So that's what a meso compound is. And so let's continue on. So here's like the flow chart that you can use. I usually didn't use it. Well, I guess I did use it, but I didn't use it in this exact way because I just looked at it. I said, are they constitutional isomers? No. Do they have a chiral center? And if they do, how are those chiral centers related? And then you would just go along with this, okay? Okay, so another thing to talk about is how enantiomers react to plane polarized light. So generally, enantiomers have the exact same physical properties, the same boiling points, the same melting points, all that stuff. The only way enantiomers really differ as far as physical properties go is how they rotate plane polarized light. So they can rotate plane polarized light either clockwise or anti-clockwise, and this has nothing to do with the R or S configuration at a chiral center. Okay, this is completely different. If you've heard of D versus L, this has to do with that essentially. Like if you've talked about amino acids before in a separate class, they use D and L because of the plane polarized light thing with enantiomers. Okay. So dexteratory means positive, levoratory means negative. I always thought levoratory was negative. Like the way that I remembered it is L, it's looks like a negative sign, so it's negative, it's counterclockwise. Dexteratory. Dexterous means right in like Greek or something. I don't know. Khan Academy told me that once. And so that means clockwise and it means positive. That's just how I remember it. You can use any mnemonic you want. And so let's look at the difference between R2-bromobutane and S2-bromobutane. R2-bromobutane rotates light in the counterclockwise direction 23.1 degrees. S2-bromobutane rotates plane polarized light 23.1 degrees in the clockwise direction. Okay? And you notice something. They rotate light the same amount, but in opposite directions. So if I had the same amount of each enantiomer, they would cancel out and not rotate light at all. Because when you add a positive number to a negative number, you get 0, and that's no rotation. And that type of mixture, where you have two enantiomers at the exact same quantities, is called a racemic mixture. And just to reiterate, racemic mixtures are optically inactive because they do not rotate plane polarized light. Enantiomers are optically active because they do rotate plane polarized light. Okay? And so then let's talk about the difference between enantiomers and diastereomers. Diastereomers can have different melting points and different physical properties. So like you can see here, A and B are enantiomers, A and B are diastereomers of C, and C has a different melting point, solubility, and all that stuff. But C does not rotate plane polarized light. Okay? So let's look at the actual formula for this thing. So specific rotation, it's the actual amount that something will rotate light. So like, for example, what you're given in like a textbook would be the specific rotation. So you see here, cholesterol has a specific rotation of negative 31.5. That would be this, okay? This alpha here is how much rotation you see, and that's dependent on the length of the sample tube, which is L here, and the concentration of the sample. A few questions I could see them asking are, what is the specific rotation? What is the concentration? Or maybe what rotation would we observe? So this is just like regular algebra. You just plug and chug. I personally don't remember a lot of these questions on any of his tests, but he will probably end up asking 1 or 2 questions overall about optic activity, specific rotation, and all that stuff. And then one more thing about enantiomeric excess is, let's say that we have a mixture of one enantiomer and another, but their amounts are not equal. That means that that mixture will still rotate plane polarized light because there's more of one enantiomer than the other. So that's where enantiomeric excess comes in. So the specific rotation of a mixture over the specific rotation of the pure enantiomer times 100% is how much more of one enantiomer is present over the other. So like if the mixture, I don't know, had a specific rotation of 20 and the specific rotation of a pure enantiomer was 30. You would have an enantiomeric excess of 66.6%. So you have 66.6% more of one enantiomer over the other. Okay? Okay, so I think that's about it for this. One more thing here. Different enantiomers will have different chemical properties. So you've heard of side effects in a lot of medications. Those are usually due to different enantiomers being present. So like let's say that you had, I don't know, something to help headaches, but a side effect would be it gives you stomach aches. And that has to do with one enantiomer helps you with your headaches, and one enantiomer makes you have a stomach ache. And that's where these side effects come from. Somebody asked, can we do some test-like practice problems for chapter 5? So let me think. One question that I know that I haven't asked yet would be they would give you a name and then ask you to draw it. So let's say that we had 2R, 3S. Sorry, I'm coming up with this off the top of my head, and I need to make sure that the chiral centers that I've designated here are in fact chiral centers. So let's say that we had 2 chloro, 3 isobutyl pentane. I don't want to draw too many. So what I always did when I looked at names here, what I would do is I would first look at the parent name. So we know our parent chain is going to be pentane. So I just go 1, 2, 3, 4, 5. And I usually end up numbering it just for my own benefit. So 1, 2, 3, 4, 5. Okay, so we're done with the parent name because we have that written down. So the next thing that I would look at is the 2-chloro, 3-isobutyl. What that means is we have a chloro on 2, so chloro on 2, that means right here, and an isobutyl group on 3. Do we all remember what an isobutyl group is? It's just an isomer of butyl. And so then we have these groups here, and it tells us what our stereogenic configuration is there. I always did this last because I like to make sure that I got the general structure right, and then went into my my chiral centers and stereochemistry. So I'm going to mark down here, this one is going to be R, this one's going to be S. Okay, and just to remind myself, R means I'm going to go clockwise, S means I'm going to go counterclockwise, like that. So R, S. And so what I'm going to do here is I'm going to label these priorities here, and I'm just going to do it one at a time. I'm going to do the one on 2 first. So chlorine is obviously going to be my first priority. This big group here will be my second priority. And then this one here will be my third priority. Now, if this is already R, which it is, then we're good. We can just put chlorine on a solid wedge. So that's what I'm going to do here. I'm going to make chlorine be on a solid wedge. Okay? However, let's say that instead this was S, and since this is going clockwise, all we would have to do is put chlorine on a dashed wedge. Because remember, we have a hidden hydrogen right here on a dashed wedge, and if that fourth priority is not on a dashed wedge, then we invert the stereochemistry. And so here we have 1, 2, 3 going clockwise. If we wanted to go counterclockwise, all we would do is make chlorine go on a dashed wedge. Okay? So now let's look at this next one here. This next one here we want to be S. And so I'm just going to assign priority. This group here is going to be 1 because this guy here, this carbon here is attached to a chlorine and neither one of the other ones are. And then the next one would be this group here, because if we follow our carbons, we see this one is exactly the same as this one, but then this one here, this next carbon, is attached to 2 other carbons and 1 hydrogen. This guy's attached to 3 hydrogens. So then this big group here is going to be our second priority, and then this will be our third priority. So now we go 1, 2, 3. It is already going counterclockwise, so all we do is we draw this as a wedge. Okay? Does that make sense to everybody? That's how you would draw something if given the name, okay? So it's just like you did before, except now you're just throwing in R and S configurations. Again, if this instead wanted the R configuration and it's going in the counterclockwise or S direction, all we would do is make this solid wedge into a dashed wedge. We would just go like this. Okay? But again, that's not the answer. This is like the actual correct answer. Okay? Does anybody have any questions on that, or does that all make sense? Okay, good. It makes sense. Do you guys have any specific questions, or should I go on to chapter 6, or do you want to go over some more stuff about chapter 5, just general thoughts about it? Because I know chapter 5 is a really hard chapter for a lot of people. I know personally I struggled with it quite a bit because it was really hard for me to understand what was happening when we did the RS configuration until, okay, so I'm going to show you a really cool site. I know I'm using Bing, but that's because it's easier to draw on. So I like to use MolView. So like for example, if it gives me a, let me close this. My thing is in the way. So if it gives you like a specific that's not what I wanted, like a specific structure. So let's say instead of this structure, it gave us that pentane structure before, or just any structure. I could just draw it like this. Let's do that, and then we'll put on this guy right here. It doesn't matter what I'm doing right now, as long as I just put something here. And then we can go click this 2D to 3D. And it will show us what this molecule looks like in 3D. So we can see here how we have, so here we have our pentane group in the middle. Here, let me annotate again. So here we have our pentane group in the middle. One, two, or not pentane, but our 4-carbon group, so that would be butane. So 1, 2, 3, 4 here. And then we have this chlorine here towards us on our solid wedge, and then our other methyl group behind us on a dash wedge. So it matches what this is. I really recommend MolView if you're having trouble looking at things in 3 dimensions. And then what you can do with this guy here is you can just rotate him any way you want. So it makes it more sense. Like if you look here, now we just rotated it. So our methyl group here is on a solid wedge, and then our chlorine group is on a dashed wedge. Okay? I really, really recommend this. If you're having trouble, it helped me personally a lot. Okay? So I'm going to go on to chapter 2. Chapter 2 is more of an overview chapter about what we're going to do next. So this type of equation right here, this type of reaction, this is called a radical reaction. This is probably the last type of reaction that we're going to cover in this class. But essentially what's happening here is this carbon is turning into a radical, and then a hydrogen gets replaced by one of the BRs. Okay, again, this is something that you'll go over later. I wouldn't worry about it too much. Just know like what generally kind of reaction this is, a radical reaction. Okay, so let's look at how we write this reaction. So what we do here is we have our reaction arrow right here, which is a must-have in every single reaction. We have our first reactant here, then our second reactant here. So we could rewrite this whole thing. Instead of having one arrow right here, we could have one arrow right here with our CH3 MgBr, and then our intermediate, and then we would have H2O, and so then we would have a 2-step reaction. It's just they're condensing it down to this one because the intermediate isn't as important as the final reaction, the final product, okay? So that's generally like how we'll write reactions. This is a type of reaction that you don't have to know yet. That's Orgo 2 stuff. So there are 4 different big types of reactions. What we're mostly going to be looking over in Orgo 2 is addition, elimination, and substitution. The first thing that we will be looking over in chapter 7 are substitution reactions. And essentially what happens in a substitution reaction, let me scroll down a little bit because I want to go in a little bit different order. In a substitution reaction, It'll show me. Okay, I guess not. We're just replacing one part of the molecule with another part of the molecule. So let's say that I have, I'm going to use this page right here. Let's say I have this guy right here with Cl plus OH negative. That Cl gets replaced by the OH negative. This is a replacement reaction. Okay? So what's happening here is we're not gaining or losing any bonds. We're replacing a bond that we had before. Okay? However, when we're talking about elimination reactions, we get rid of 2 sigma bonds to form 1 pi bond. And what that means is we're getting rid of 2 single bonds to form a double bond. Because if you think about it, both of these carbons, to make this double bond, need to get rid of something because they can't have more than 5 bonds. So they get rid of X and Y and they make that double bond. And so then, oh, here's substitution. I totally scrolled right past it. But this is just more examples of it. It's honestly easier to see. One thing that got me on my test, I remember here. So like, let's say that we had this guy right here and it transformed into this guy right here. This is not an addition reaction because there is no double bond being added to, and instead this is a substitution reaction because we're replacing a hydrogen with a bromine. In addition, this example here, this is a addition reaction because addition is the opposite of elimination. We're getting rid of a double bond here and we're adding 2 single hydrogen bonds. But remember, we don't always draw the hydrogen bonds in line angle structures, which is sometimes why it can be confusing. So those are the main ones that we'll go over. There are different types of reactions. So like when we get into substitution, there are 2 main types of substitution reactions. One that is a concerted reaction where everything happens in a single step, and another one where it happens in 2 steps, which is called a stepwise reaction. Okay? And so all of this is generally just an introduction to how reactions work in organic chemistry, because it's a little bit different than Gen Chem, because we often use arrows to show the mechanism of a reaction, which is to say that we use arrows to show the movement of electrons. Okay, and we saw that a little bit in the acid-base stuff. Okay, and there are 2 different types of bond cleavage: homolysis and heterolysis. Okay? Homolysis breaks the bond evenly, each one gets 1 electron. Heterolysis, it breaks it unevenly, one of them gets all of the electrons, one of them gets none. In a homolytic cleavage, we end up with 2 radicals because a radical doesn't really have a full charge, because to get a full charge, you need a full pair of electrons. Because remember when we do, so like if we look here, this guy and A and B cannot have a formal positive charge or a formal negative charge, because you can think of this this bond here as a full negative charge. And since neither of them get the full bond, they're both end up with an overall neutral but not really radical. Okay? However, in heterolytic cleavage, we end up with one of them getting all of the electrons, so A in this case, B in this case, and getting all of that negative charge and being overall negative. On the other hand, the one that didn't get any of the electrons ends up as positive because they don't have any electrons and end up overall positive. Okay? Mostly, we're going to be talking about heterolytic cleavage. Again, we'll talk about homolytic cleavage when we talk about radical reactions, because again, to get radicals, we need to do homolytic cleavage. Okay, so here are the different types. So when we're talking about carbocations, carbon ions, radicals, these are sort of important words that you're going to hear a lot. Specifically, you're going to hear the word carbocation a lot, because most of the time, Z is going to end up being more electronegative than C, and it's going to pull those electrons towards itself and away from that carbon, and we're going to end up with a carbocation and something else with a negative charge. Okay? And homolysis, usually homolysis will occur when there's already a radical, or if we are putting in light or heat. Okay? And again, we'll explore this more when we end up in later chapters. Okay. Bond forming. So this is important because it shows you an example of how arrows will work. Here we can see, I always like to think of it as each head of the arrow represents one electron. So if I have an arrow right here and it only has one head, one little part of it, like in these arrows here, that's going to take one electron with it, okay? On the other hand, if we have two heads on it, like this arrow right here, it's going to take two electrons with it, okay? It can be hard to remember sometimes. Just make sure to make your arrows, if they're moving two electrons, very obviously two-headed arrows instead of a half-headed arrow, okay? Okay, and so bond dissociation energy, again, this is stuff that you should have gone over in Gen Chem. If not, that's totally fine though, although we don't focus on it too much in Orgo. So you can see here that we can have an endothermic or an exothermic reaction. The endothermic, you put energy in, the exothermic, you get energy out. Which one is preferred? The exothermic, because you don't have to put in light or heat for it. And bond dissociation energy, just, this is Gen Chem stuff. Again, I don't think you would be asked to calculate an overall enthalpy change. You're more likely going to be given this graph and to talk about that graph. But I would know how to do it. So like the enthalpy change is the sum of the delta H of bonds broken plus the negative delta H of bonds formed. I like to think of it if like you break a glow stick, it's going to release energy in the form of light, and that's what's happening here. When you break a bond here, it's releasing energy, so you have positive energy. And when you make a bond, you're losing energy, so it's negative energy. Okay? So bonds broken minus bonds formed in this class is going to be our delta H. And then another thing that's talked about in Gen Chem is the overall chaoticness of a situation, which is called the entropy. The more chaotic a system can be, the higher it will be in entropy. So in this example here, we go 1 mole of a reactant to 2 moles of products. The entropy goes up because the overall chaos goes up. Here, on the other hand, we have 2 reactants making 1 product. The entropy goes down because our general chaoticness goes down. Okay? Okay. You can think of it as if you have 2 marbles, they can roll around everywhere, but if you have those 2 marbles stuck together, they can't roll around as easily. And then here's the Gibbs free energy formula. I don't think you have to have it really memorized in class. In this class, for example, it's more Gen Chem stuff, but generally you can think of it as delta G is about delta H because our temperature is going to be relatively low most of the time. Okay? Okay. Equilibria, again, organic chemistry overall is more about the concepts rather than doing math, if that makes sense. I personally did not have too many of these math problems, just generally know how to solve them if it's given to you. The most important part, I personally think about this chapter specifically, is going to be talking about how these reaction coordinate graphs work and how a catalyst works, because he might ask you, oh, what is the catalyst in this reaction? Generally, the catalyst is going to be listed above and it's going to remain unchanged. So instead of being listed above right here, we could have H2SO4 over here plus H2SO4. The H2SO4 remained unchanged, so it's going to be considered the catalyst. Let me see if there's a little bit more. Oh, and catalyst lower the energy of the transition state, not the actual reaction. So it lowers the activation energy, so it promotes the reaction going forward, but it doesn't change the equilibrium. Okay? So I'll leave you guys here. Since we did not go over any of this stuff in class, I think I went kind of far ahead. But the difference between kinetic reactions and thermodynamic reactions is kinetic reactions are fast, thermodynamic reactions are stable. Okay, that's the main takeaway from these. Okay, yeah, so I think I'll let you guys go. If you guys have any additional questions, just let me know. Again, you can shoot me a message through GroupMe or through web courses. Either one, I'll see. Okay, so I'm going to end my office hours there. Again, let me know if you guys have any other questions.